All right, so today we're just going to introduce the concept of vectors. Some of it will sound familiar to you already. We're going to talk about how do we identify and draw vector quantities, what happens when we have more than one vector in both one direction and in multiple directions, and then how do we solve this graphically, okay? So that's kind of the layout for today. So let's start at the top. So there's a scalar quantity and a vector quantity. So a scalar quantity is any quantity in physics that has magnitude. Okay, and I'm like, what does that mean? Okay, so meaning it has some number value with units. It has a number and a unit. Okay, so if we're looking at some examples here, speed, we've talked about speed and velocity and the difference between them, right? That was from the last unit. So we know speed is a scalar quantity when it has a number and a unit. So let's just say 10 meters per second. So an example here is a scalar quantity of speed going 10 meters per second. That's a number and a unit. If I'm looking at 25 meters, what's that? I hear it, distance. So 25 meters is a unit of distance, which is a scalar quantity. And then age. Age is a number and a unit also. It's still a quantity, and it's a scalar quantity, so like 16 years old. Okay? So those are some examples of quantities that have a magnitude, meaning a number value and a unit. Okay, and this is a little different than a vector because a vector quantity is any quantity. Ooh, I just spelled quantity wrong. Quantity in physics that has both magnitude and direction. And this is what we talked about last unit, when speed versus velocity. So meaning that it has some number value with a unit and direction. So now it's a number, a unit, and a direction. So if I'm looking at velocity here then, compared to speed, how could I say that my speed is actually a velocity? 10 meters per second, and I need a direction, right? So pick a direction. West. Okay, so 10 meters per second west is now a velocity. It is a vector quantity. I have a number, a unit, and a direction. Okay, before I had 25 meters as a distance. Well, now if I say 25 meters east, this is a displacement. And a displacement is a vector quantity. Real quick, I'm going to put the v in parentheses and x in parentheses, and acceleration is a in parentheses, because those are our one-letter symbol for velocity, displacement, and acceleration. Okay, acceleration. Well, what's the acceleration due to gravity? 9.8 there it is, meters per second squared, and we can just give a direction down or south or whichever one, just an acceleration and a direction. Okay, so the difference here is we're really focusing on the direction part. Note about direction though, it can be in terms of degrees or cardinal directions. It's kind of hard to see on the paper, but that is a circle, right? So 0, 90, 180, 270 degrees. So we can indicate the direction by using a degree. or we can indicate it using the cardinal direction. So north, south, east, west, but then also like, you know, northeast, southeast. You can get even more specific and say like north, northeast or east, northeast. So you can get even more specific that way. Okay, so then how do we identify them? So if I'm looking at a symbol, how do I know I'm talking about a vector? So vector quantities can be identified with an arrow, or really a half arrow, above the symbol. So in this example here, I have a velocity, and you see the arrow above it. That's telling me that this is a vector quantity of velocity. 23 meters per second northeast. So I have a number, a unit, and a direction. Okay, well, if we did displacement, we would have an X with an arrow above it. And you're really going to see like a half arrow a lot. So that would be like a displacement or acceleration. Same thing, an A with an arrow.
When we're showing our work, do we have to put the arrow too?
Yes, if it is a vector quantity. Good question. You do have to show the arrow. When we get there and we do force, the force would also be a vector quantity. Okay, so when we're just talking about a resultant vector, meaning what we get when we add them together, a lot of times you'll see that written as an R, capital R with a half arrow for a resultant. Okay. There's also another way, so we've got a symbol with an arrow. Well, then we can also represent vectors by drawing arrows themselves. So drawing arrows. So when we're drawing an arrow, the length and direction of a vector should be drawn to a reasonable scale size. I'll explain what that means in a second. And show its magnitude. So if I'm going to draw my arrows to represent my vectors, the length and direction of a vector should be drawn to a reasonable scale size when comparing them to other vectors. And you have to list its magnitude. Remember, magnitude is a number in a unit, okay? So take a look at these two. We've got an arrow heading east that says 20 kilometers. This is an example of a vector arrow. I've got my magnitude, 20 kilometers, and my direction. And then I have another one that says 10 kilometers with an arrow also heading east. But are these the same size arrow? No. So this is what I mean by the length. And the scale size is 20 kilometers is bigger than 10. So my arrow to show that as my vector is bigger than the 10. Okay, so that's what we mean when we are talking about a reasonable scale size. Okay, great. So what am I going to do with these? Well, vector application. When two or more vectors point in the same direction, you can add them together when they point in the same direction. So indicating here that we have two or more vectors in one dimension heading in the same direction, we can add them together. So if I'm looking at this first example that you've got on the page, 46.5 meters east, and then I've got another vector heading 20 meters east. I can add these together to get my total for these two vectors because they're heading in the same direction. So I'm just going to draw like an arrow from the first point to this picture so that way we know they go together. So if they head in the same direction, we can add them together. But what about when two or more vectors point in the opposite direction? So if they're in the opposite direction, what do you think we're going to do? Subtract. Good. Okay, so if they're heading in the opposite direction, it's like they're opposing each other. We're going to subtract. So if I look at the same ones I had before, but now there's one pointing in the opposite direction, I'm finding the difference between them, and that is what's called your resultant vector, okay, or what you get at the end. Okay, so looking at this, there are two practice questions, 1 and 2. So take a minute and look at what you've got, figure out what you're gonna draw. Remember, you have this reasonable scale size arrow to represent that vector, and you need a magnitude and your direction to indicate that quantity. So take a minute and solve 1 and 2. All right, let's go ahead and go over number 1 and number 2. So number 1, I have 7 meters east, 4 meters east. Are they heading in the same or opposite directions? Same. So what are you going to do? Add them together. So when I draw my resultant vector, what am I going to draw? A big arrow to the right, yeah? And what is its magnitude and direction? Perfect. And this is what I mean by scale size. The 7 meter vector is bigger than the 4 meter vector, and the 11 meter vector is bigger than both. Okay? So now let's look at number 2. Number 2, 9 meters per second south, 5 meters per second north. Are they heading in the same or opposite direction? So what are we going to do? Okay, so what am I going to draw? A big arrow, medium arrow, or smaller arrow? Okay. Smaller, because it needs to be smaller than this one and that one, because it's the difference between them. So what is my magnitude and direction? Perfect. Okay, thumbs up. Did you get both of them right? Brilliant. Okay, well this is really awesome when they're all in one dimension. Yeah? Because we just add and subtract. But they're not always going to be just in one dimension. So if then the vectors or vector quantities are in more than one dimension, we can separate the x and the y components of a vector. So we can look at the resultant and separate it into an x and a y component, or we could take the x and the y component and find the resultant. Okay, so we can determine what these are using graphs or ruler measurements. So if I'm looking at this baseball that's flying through the air, what I really have here is, and I'm going to add to this picture, is my symbol is a velocity vector, and this is my resultant vector. So that capital R right there is telling me that it's the resultant. It's what I'm getting from my x and y components. It's what I see in my motion. Well, that's made up of an x, so we have a velocity in the x direction, and then we have a velocity in the y direction. And these two components make up my resultant. So I have the arrows telling me that it is a vector quantity of a velocity in the y direction. Okay, so the notation is really important. Okay, so go ahead and flip this up because there's more to talk about here. So let's look at the graphical method. So what am I going to do? How am I going to solve this? Okay. How am I going to solve this? So we're going to use what's called the head to tail method, and it's how you draw them. Okay, head to tail. So aligning vectors. Sorry there, head to tail. Aligning vectors head to tail, and then drawing the resultant from the tail of the first vector to the head of the last. Okay, what is this head to tail business? What's this mean? So if I'm drawing a vector, I start somewhere, I draw it in a specific direction with an arrow. Okay? This part is called the tail of the vector. This part is called the head of a vector. Okay? Okay, so then if I am looking at this picture, I'm starting down here, and this is the tail of this first vector. The head to tail method means that I line them all up and I stack them up from tail to head, tail to head, tail to head. And then after you do that, you can find your resultant vector by connecting the very tail of the very first one to the very head of the very last one. This is what that head to tail method is, okay? So let's apply this then to this practice question. There are some steps here that we can use, and let's apply it to the practice question. So a person travels 2 city blocks north, 4 city blocks east, 2 blocks north again, 2 blocks west, and 2 final blocks north. Draw the path this person traveled and draw the resultant vector. Okay, well, the very first thing I need to do is figure out my directions, right? Isn't this dependent on directions? So I'm using north, south, east, west, so that's cardinal directions, yeah? So right here, I'm just gonna write north, south, east, west. So that way when I am sending my little stick figure on his journey, on their journey, excuse me, we can point them in the correct direction, okay? The next thing is I need a scale. So if I'm talking about a city block, then wouldn't it make sense that one of these segments is representing a city block? Why make it harder on ourselves? Yeah? So I needed a scale, check. I needed directions, check. Okay, now I'm going to go stepwise, each vector at a time, and draw it in on my paper. So the first one, 2 city blocks north. So if we're traveling blocks, is that going to be like a velocity, an acceleration, a displacement? Is that a velocity? What is it? Exactly. So we're looking at displacements here, just so we keep that in our brain, okay? So I'm starting with my friend right here. The first thing I'm doing is traveling 2 city blocks north. So from this would now be my starting place, or the tail of the vector. I'm going to travel 1, 2 city blocks north. This is the first vector from this description in the question. Okay, so I'm going to put a little check mark because I just drew that one in. Next, they traveled 4 city blocks east. So head to tail method. I don't start back where he was, or our friend was. I'm starting where they are right now. Yeah. So where they are right now, I'm going to start here and travel 4 city blocks east. 1, 2, 3, 4. That is the second vector. Okay, if I'm looking at my question, the next one says 2 blocks north again. So I go from where our friend is right now, which is at the head of the second vector, and I'm going to go 2 blocks north. 1, 2. Well, then our friend goes 2 blocks west. So starting here, 2 blocks, 1, 2, heading in the west direction. And finally, 2 blocks north again. 1, 2. Okay. That is the path that our friend took. Well, now we're going to figure out the resultant displacement. I'm going to use a ruler. And what we're going to do, just watch, is we're going to connect from where did we start originally to where did we end at the end of the journey. Okay, and then it's just like a bird's eye view between the two. This is my displacement resultant vector. So yes, this may be the path that our friend took in the city, but this red line is our displacement resultant vector. All right, so now we're going to look at some examples here. This is taking a resultant vector and finding its components, and then you will also have the components and then find the resultant. So you'll go back and forth, okay? It's gonna feel a lot like a whole lot of triangles, okay? And what we're doing is determining the X and Y components of each. So using our two different colors, we are going to look at the examples and identify our X component and our Y component. So I'm gonna use blue for the X and I'm gonna use red for Y, but you can choose whichever two colors you want, okay? So number one, the first thing we need to do though is determine what our symbol is going to be, and that's going to be from the units. So 7.1 meters. Well, meters is a unit of distance, and the vector of that is displacement. So what we're going to use here is X with the half arrow, because that's going to be our symbol that we use for this vector, okay? Which means that this right here, which is my resultant vector, I'm going to label it as X with a capital R and a half arrow, indicating that this is my vector quantity of displacement and it's the resultant. The capital R is the resultant. Okay, and now it's kind of like a puzzle. You have to think about the head to tail and where do we start? Which way do we draw the arrows? Okay. Well, you can do this a couple of different ways, but I am starting here. We know that we start here at the very bottom, and we know that we end at the head of this vector. So I'm going to draw an arrow in my X direction over to where it would stop. Okay. And in this assignment, we're going to use the same cardinal directions, north, south, east, west. And it says in the direction that one box or each square is representing one of whatever unit we're in. That just makes it easy on ourselves, okay? So this first one right here is the displacement vector X component. So off to the side, I'm going to write this, which looks a little strange, but it is the displacement vector X component. And I need a value for this, so I can just count how many boxes I went. 1, 2, 3, 4, 5, 6. 6 meters. And if I look at my cardinal directions, north, south, east, west, I headed in the east direction. So my X component of this displacement vector is 6 meters east. It's like you're finding the other sides of the triangle, okay? Well, from there, though, I went up. From there, I went up, so I'm using my other color. So of my displacement vector, this is my Y component. So to actually find this, my notation here is my displacement vector in the Y direction equals, and I'm just going to count 1, 2, 3, 4, 5. 5 meters. That's my magnitude, so my number and my unit, and then I need my direction. What direction is it? North. There we go. So I have the resultant, and I broke it down into my components of that vector, and I identified what the magnitude is, which is the number and the unit, and then the direction. Okay, one thing I want to point out to you is hop on over to number 5. Is this 1-dimension motion or 2-dimension motion? Is there an X and a Y? No. Is it just a Y? Okay, so, and since it's kilometers per hour, I'm using a velocity as my notation. It's a velocity vector. So this is my velocity resultant vector, but it happens to only be in one direction, yeah? So I'm only traveling in this one direction here. So that is my velocity in the y direction, which is 4 kilometers per hour north. Because it's only one direction. Is there an x component? Nope. So I'm going to say, well, my velocity then in my x direction is 0. Okay. That's an arrow, sorry. So that's how we're going to look at the resultant vector and then break them down into the components with the correct notation.